Now I would like to introduce the concept of acids and bases. First, let's start with a couple of definitions so we can understand what acids and bases are. Now, I realize you might have seen some of this stuff before, but I really want to go down to basics. There are three major definitions of acids and bases that we're going to learn about in this chapter, and I want to start with the simplest and narrowest. That is the Arrhenius concept. So the Arrhenius concept simply defines an acid as a species that produces an excess of protons in water. So the hydrogen ion, the hydrogen plus one ion, is simply a proton. If you remember the hydrogen atom, it consists of a proton and an electron. And if we strip away the electron to make the cation, all we have left is a proton. So saying H plus and saying proton, those two are synonymous terms. So an acid is a species that produces an excess of protons in water in the Arrhenius concept. An example of this would be, for example, hydrochloric acid. If we put hydrochloric acid in water, I'm just going to put the water over the arrow, it completely dissociates into protons and chloride ions. So that complete dissociation makes a lot of protons float around in the water. Those are aqueous ions. And there we go. We have the Arrhenius definition of an acid in hydrochloric acid. It's also very simple. The Arrhenius concept is also simple when we're defining a base. In the Arrhenius definition, a base is a species that produces an excess of hydroxide ions in water. So OH minus is the hydroxide anion. An example of this would be, say, sodium hydroxide. If we put sodium hydroxide, which is a solid, in water, it completely dissociates to make sodium ions and hydroxide ions. So that species, sodium hydroxide, is going to release a lot of hydroxide ions into the water, making it a base in the Arrhenius definition. So that's the narrowest possible definition that we could have for acids and bases in general chemistry. A slightly broader definition, and maybe a more universal definition, although it's not the broadest definition, is the Bronsted-Lowry concept of acids and bases. So this is going to be a broader definition than the Arrhenius definition. Bronsted-Lowry holds that an acid functions as a proton donor and a base as a proton acceptor. So using this definition, we can more readily apply the concept to a more diverse array of reactions. For example, let's take a reaction where HOCl reacts with water in an equilibrium with OCl minus anion and hydronium. So the H3O plus ion, this is hydronium. And I could say that all of these species are aqueous. Water is liquid, but the rest of them are aqueous. So if I want to be very good, I should include always the specification of each species' state. So let's use the Bronsted-Lowry concept to classify the different species on the left side of this reaction. On the reactant side, we have HOCl and H2O. So what is going on here? Which species is giving away its proton and which species is accepting a proton? In order to assess that, we have to look from left to right. And we can see as we go from left to right, HOCl loses its proton to become OCl minus. H2O gains a proton or accepts a proton to become H3O plus. So looking at HOCl, it is donating its proton to water. So that makes the HOCl the proton donor. Water functions as the proton acceptor. So the proton donor is the acid, and the proton acceptor is the base in the Bronsted-Lowry definition. Now, on the right side of the reaction, we have two different ions, and you should know the name of H3O plus. This is the hydronium ion. So we're going to see this a lot in the acid-base chemistry. The hydronium ion is the strongest acid species in water that we're going to see in our aqueous acid-base systems. So you should know that name, hydronium. I'll talk more about this reaction in a minute, but I want to talk now about another example so you can kind of see the Bronsted-Lowry definition in action. Let's take ammonia interacting with water. Okay, so NH3 plus H2O. That is going to produce an equilibrium reaction where on the other side I get the ammonium ion and the hydroxide ion. So here, once again, let's look at the reactants and decide which is the proton donor and which is the proton acceptor. Going from left to right, we can see that the ammonia is accepting a proton to make ammonium ion. Conversely, water gives away its proton, and what's left on the right side is hydroxide. So here, it's clear that ammonia is functioning as the proton acceptor, or the base, while water is functioning as the proton donor, or the acid in this reaction. Now, here, once again, since we have a base, we are making, instead of hydronium, we're making hydroxide ions on the right side. And the hydroxide ion is notable because it's going to be the strongest base species in water. So here we are seeing in the first example, water interacting as a base. And in the second example, water is interacting as an acid. So species like this have a special name. They are amphoteric. Amphoteric species have the ability to act as an acid or a base. And water is a great example of an amphoteric species because depending on what it is interacting with, water can act as a proton donor or a proton acceptor. If water interacts with a species that is more acidic than it, then it'll act as a base. If water interacts with a species that is more basic than it will act as an acid, as we saw in these two examples. Water isn't the only amphoteric species, but it is one of them. So, a few more definitions. On the product side of the reaction, so in these two examples, on the right side of the reactions, we have what's called the conjugates. So when we're defining species on the product side, that is to say on the right side of a reaction, we call them conjugate acid or conjugate base. The definition is very straightforward. The conjugate acid is whatever the species is that's formed from gaining a proton. And again, this is on the right side. Conjugates are always on the right side of the reaction relative to the acids and bases on the left side of the reaction. Of course, you can have conjugate pairs that you talk about on both sides of the reaction. It's really just a semantic issue. The conjugate base, by contrast, is the species that is formed from losing a proton. Let me show you what I mean. Losing an H plus, I guess. Let me show you what I mean with those two examples that we just did. So in the first example with HOCl, this is hypochlorous acid. We talked about how this is the proton donor, it's acting as the acid, and water is acting as a base. Well, HOCl is the proton donor, and what's left of it on the other side would be defined as the conjugate base. So OCl minus is the species that is formed from losing a proton. So every acid on the left is going to have a conjugate base on the right. Conversely, every base on the left is going to have a conjugate acid on the right. And the conjugate acid is the species that's formed from gaining a proton. So the conjugates occur in pairs. A conjugate acid on the reactant side will have an acid on the reactant side will have a conjugate base on the product side. A base on the reactant side will have a conjugate acid on a base on the reactant side will have a conjugate acid on the product side. We can also see this example with the ammonia. We can also see this with the ammonia example. The ammonia is functioning as a base and the water here is an acid. So the base should have a conjugate acid, and its conjugate acid is the species that forms when that base accepts a proton. So the base accepts a proton and it becomes its conjugate acid, ammonium, NH4+. The acid donates a proton and it becomes its conjugate base, which is hydroxide. So every acid has a conjugate base, and every base has a conjugate acid. Furthermore, acid strength is determined by the ability to donate protons. So acid strength is determined by the ability to donate protons. We can think of that in the Bronsted-Lowry definition. How good of a proton donor is this species? The better it is at donating protons, the stronger the acid. Okay, greater donation of protons, stronger acid. Now, looking at two sides of a reaction, the stronger the acid, the weaker its conjugate base. Now, this is an equilibrium idea. Okay, let me just write that sentence down. The stronger the acid, the weaker its conjugate base. This is an equilibrium idea. Let's go back to the HOCl example. The stronger the acid, the more this equilibrium is pushed forward to the right. So that depends on having a relatively weak conjugate base on the product side. The relatively weak conjugate base does not have much ability to push the reaction to the left towards reactants. So the stronger the acid, the weaker the conjugate base. And vice versa, the weaker the acid, the stronger the conjugate base. In the same way, we can state that the stronger the base, the weaker its conjugate acid, for the same reason, looking at that equilibrium. So the stronger the base on the left side of the reaction, the weaker its conjugate acid on the right side of the reaction. The less ability that conjugate acid has to drive the reaction in the reverse direction.